So we are here today to talk about the chi-squared test. What a chi-squared test allows for us to do is to figure out if the variation we observe in an experiment is due to random chance, or if that variation is due to some other cause. And the way we figure this out is we use four different but important pieces, right? We're going to use our hypotheses, which we'll go over in just a second. We'll need a chi-squared value. We'll need to figure out degrees of freedom. And ultimately, we'll need to figure out our p-value. So what do all these things mean? Well, for our hypotheses, we've got two different ones that we need. We have our null hypothesis. The null hypothesis is always that whatever we changed or whatever the different setting was between groups had no impact. So, for example, if we were rolling a dice, our null hypothesis might be that we would get number 2 just as often as we got number 6, just as often as we got number 1, just as often as we get number 4. Basically, that the number on the dice had no impact on how frequently we observed that number. 7%. We can also roll the genetic dice. For example, if I were to breed these two pea plants together, I might expect to receive offspring that was 50% tall and 50% short. Or I might expect to receive offspring that are 75% tall and 25% short. And the way we set up a null hypothesis is by saying that whatever we expected is what we observed, right? If I expected 75% to have one specific color of flower, for example, of the offspring, if I expected 75% to have white flowers and 25% to have red flowers, that is what we expect to observe, and that would be your null hypothesis. The alternate has to take care of every other possibility, every other thing that might crop up. So, for instance, in our flower example, you might expect to have 75% white flowers, right? Your alternate hypothesis would be that you don't, right? You don't have to say it's more or less. You just have to say that it's not what we expected. And so between these two, we need to cover all possibilities. All right? Let's try a few of these together. Here's our first experiment. Exposure to different music influences reasoning capability in mice. That is something you can absolutely test, right? We talked about this experiment on the first day of class. Exposure to different music influences reasoning capability in mice. One way we could test this is by using a maze, as they did in the experiment we discussed. And so let's talk about this. Null hypothesis. The null hypothesis is that nothing is different between groups. Here, our groups are going to be exposed to different music. So the null hypothesis might be exposure to different music does not influence reasoning capability in mice, as evidenced by times it takes them to complete a maze. Right? It's something we can test. And it says that there is no difference between groups. The alternate has to take care of every other possibility. All right? So the alternate might be something that's exactly the same, except that we get rid of that word not. Exposure to different music does influence reasoning capability in mice, as evidenced by the time it takes them to complete a maze. The only difference we see between these two groups is that your null hypothesis is that whatever you've treated them with does not influence the outcome, and whatever you treat them with in the alternate hypothesis does influence the outcome. Here's a very related example. Exposure to different music adversely influences reasoning capability in mice. All right, we can use pretty much the same experiment. The only difference really is going to be that our null hypothesis has to take care of everything that's not adverse. So that means the ones that had no change and the ones that got better. All right, here are our hypotheses. The null hypothesis is that we do not adversely influence mouse reasoning capability by exposing them to music. The alternate has to take care of all the other possibilities, and the other possibilities is that we do adversely influence their capabilities. All right? So in this instance, we've got a different null hypothesis than what we had in the last experiment. And the reason our hypothesis is different is because we are trying to just look at mice who did poorly. So our null hypothesis here encompasses all the mice that did okay, that did the same, and that did better. The alternate hypothesis here just cares about the mice that did poorly. All right, so you need to really consider what you are trying to test when you write the null hypothesis and when you write the alternate hypothesis. All right, so now we know how to set up our hypotheses. We know how to make a null hypothesis, right? That's where everything you expect to see, you see. The alternate is you didn't see what you expected to see. All right? To calculate the chi-squared value, we're going to use an equation. And this equation looks something like this. We will come back to this equation and figuring out how to solve for this value. But what we are going to do first is figure out how we apply it so that once we solve for it, we can use it right away. After we use our equation to figure out chi-squared, we bring that value over to what we call a chi-squared table. And this table has three main parts. Along one side, we have what we call degrees of freedom. Along another side, we have what we call p-values. And the majority of all these somewhat scary looking numbers, to be quite honest, are our chi-squared values. When you go to read a chi-squared table, you don't care about most of the table, all right? We only care about the part of the table that would apply to our experiment. And so to figure out what part of the table we are talking about, we're going to start with a discussion of degrees of freedom. You calculate degrees of freedom using this equation, n minus 1, the number of groups you have minus 1. So if we were talking about flowers, right, white or red flowers, we've got two groups, white and red. Two groups, 2 minus 1, our degrees of freedom would be 1. Once you figure out your degrees of freedom, right, in our flower example it was 1, you only care about the numbers underneath that amount of degrees of freedom. If we were talking about rolling a dice, right, a dice has 6 sides. That's 6 groups. 6 minus 1, 5. We'd only care about this column. Once you figure out your degrees of freedom, you can ignore everything else except for that column. So in our example, right, in our example with the flowers, we have 1 degree of freedom. All of this stuff no longer matters to us, right? We can cross it out, all right? All we care about are the numbers you can find here. And if you recall, this is where you'd expect chi-squared values to be. And you can calculate those chi-squared values using the equation that they give to you on the AP equation sheet. All right? So if you figure out how many degrees of freedom you have, you just care about the group down below. Okay, so what you see here is the table we had before, but we determined that n minus 1, the number of groups minus 1, was just 1. So our degrees of freedom is 1. We no longer care about the rest of this table. All we care about is what's happening in this column. Now, we had 1 degree of freedom. These are possible chi-squared values. If when you do the math out, you get 1.32, that's the one we're going to care about. If you get 2.71, that's the one we're going to care about. But the chances of you getting a chi-squared value that's exactly what's on this table are kind of slim. But what you can notice if you look at this list is that we increase as we move down. And so what you'll be able to do is find either a place you belong between or a side of this list where you belong. So if you had a chi-squared value of 2, you'd know you'd fall between these two values, and we'd care about what happens in those two values. If you have a chi-squared value of 3, you'd know you're between these two ones. If you have a chi-squared value of 4, you know you're somewhere in the middle of there. And so what you want to do is find approximately where on this table your chi-squared value belongs. All right? Let's say our chi-squared value, for the sake of our discussion, if our chi-squared value is 3, right? That means that your chi-squared value falls between these two numbers. So what we're going to care about are these two numbers, right? As soon as we determine this is where our chi-squared value is, we no longer care about what's happening up here, And we no longer care about what's happening up down here. So here's where we stand right now. We had a degree of freedom, which came up to 1, so we only cared about this column. We had a chi-squared value of 3, which means we only care about the numbers on either side of 3. Just like before, we can narrow it down. This part is not relevant. It's not matching up to our chi-squared values. These parts, not relevant. They're not matching up to our chi-squared values. So what we can tell is that if we had a chi-squared value of 3, you fall somewhere between a p of 0.1 and a p of 0.05. It's greater than 0.05, but less than 0.1. Probability is a tough thing to really understand. So let's try and give it some context. If we have a p-value of 0.1, right? What that means is that if you did this, whatever you tested, 100 times, you expect to get the result you got 10 times, right? 0.1 times however many times you did it. The probability of getting that outcome any given time is 0.1. Put another way, that means that you've got a 10% chance that whatever you observed was just random variation, right? If we're talking about flipping a coin, there is a 10% chance that the number of heads and tails that you got was just randomly the result of natural chance, right? That means that there's a 90% chance there was a difference between groups, right? 90% sounds quite strong. In science, we have sort of an arbitrary cutoff of what is, a sincere difference. We consider a p-value of 0.05 to be significant. If p is 0.05 or smaller, that means that you've got a 95% chance or higher that what you've observed is a genuine difference between groups. And so if you have a p-value that's quite low, and by low I mean 0.05 or smaller, if p is low, HO must go, right? So if p is 0.05 or smaller, we can get rid of that null hypothesis. The only other option besides the null hypothesis is the alternate. So if the p-value you calculate is 0.05 or smaller, what you're going to do is reject the null hypothesis. You're going to say the null hypothesis was wrong. All right. So I said we'd get back to using that chi-squared equation, and we're back, all right? We've got two different versions that we're going to try. We're going to try testing flowers and flipping a coin. Let's start with the flowers. We expect 75% of the flowers that bloom to be red and 25 to be white. If you have 100 flowers that grow, that means that 75 we expect to be red and 25 we expect to be white. The E, or expected value, that's what you predict, right? We have to be able to predict an expected value in order to use this type of test. We also need to be able to observe what happens, and that's what the O stands for in our equation. So let's figure out what we observe. If we actually observed 70 red and 30 white flowers, that sounds pretty close to what we were expecting, but it's not quite the same. There's more white than what we were expecting. To figure out if that number is significantly different than what we expected, we're going to have to calculate our chi-squared. So to figure out our chi-squared value, we need to figure out observed minus expected squared divided by expected for each group, and then add it up. All right? So let's figure out observed minus expected for our red flowers. What we observed was 70. What we expected was 75. We can square that difference. Divide by expected, which was 75. Let's take a look at white. What we observed was 30. What we expected was 25. You can square that. And divide by what we expected. What we're going to have to do is add those values up. Once we do the math, 70 minus 75 is 5. Square that, that's 25. 25 divided by 75, and we get 0.333. When we do the math for the white flowers, we also end up with 0.333. This is basically how far off we are from what we've expected for those groups. What we need to do to figure out our chi-squared value is add these two together. 0.333 plus 0.333 equals 0.666. Now we have our chi-squared value of 0.666. The only other piece of information we're going to need in order to use our chi-squared table is the degrees of freedom. Here we have two groups, red or white, and 2 minus 1 is 1, so that means we have 1 degree of freedom. Welcome back to our chi-squared table. You can see I've already narrowed down our degrees of freedom to 1. What we need to do is figure out where on this table 0.66 would belong. What you can see is the top of this table are small numbers and it gets bigger as you go down. 0.666 does not fit between any two of these numbers. But because we know the trend on this table, we know that it would belong somewhere up at the top, somewhere above 1.32. So what we are going to focus in on is whatever p-value is associated with 1.32. So that means we know that our p-value has got to be greater than 0.25. P is greater than 0.25. That means P is high. If P is high, that means that there's a high likelihood what we see is due to random chance. So that means that we are going to fail to reject the null hypothesis. It might be that this is something genuine, but we do not have the evidence needed in order to reject the null hypothesis. Let's try another example. If I were to flip a coin 50 times, and I believe that there's no difference between how frequently I get heads and how frequently I get tails, we're going to say that our expected value is that half the time I get heads and half the time I get tails. Half of 50 is 25. Half of 50 is 25. What I actually ended up observing, was that I got 10 heads and 40 tails. That looks like a pretty significant difference to me, but I'm going to need to use my chi-squared test to make sure that it's not just random variation. So let's try and figure out our chi-squared value. We need observed minus expected squared divided by expected. This is the equation you see for heads. This is the equation you see for tails. Once you do the math out, this comes out to 9. This also comes out to 9. But as you guys know, these are not numbers that we leave on their own. We're going to have to add these guys up. Once we add 9 plus 9, you get 18. So that's our chi-squared value. All right? In order to use our chi-squared table, we're going to need to know degrees of freedom. We have two groups. 2 minus 1 is going to give us our degrees of freedom. It is still 1. We are back at our chi-squared table. As you guys know, we cross out everything that we are not dealing with. And so since we only have 1 degree of freedom, I don't care about this part of the table, right? What I care about is just the 1 degree of freedom portion of this table. And as you guys know, our chi-squared value should be somewhere around here. Our chi-squared value was quite high. When your chi-squared value is high, what that means is that there was a lot of variation from what you expected. If things are very different than what you'd expect that the probability it was random, not so strong. The probability it was a genuine difference you observed is going to be higher the more different your results are from what you'd expect. So, since we had an 18 as our chi-squared value, it would fall somewhere below this. Somewhere below this chi-squared value, meaning that our p-value would be something smaller than that, right? Our p-value is less than 0.001. That's pretty significant. If p is low, HO must go. So the chi-squared test is actually pretty simple, right? You develop your null hypothesis and your alternate hypothesis, calculate your chi-squared value, figure out degrees of freedom, and use those two pieces of information to determine your p-value. If your p-value is low, and by low I mean 0.05 or less, we can reject the null hypothesis. If your p-value is high, and by that I mean higher than 0.05, you are going to fail to reject your null hypothesis. You don't have enough information to say that the variation was not random. The other way of testing for chi-squared is right here. What? All right, good luck, guys.